We're going to do 5.4, analyzing graphs of polynomials. In the last section, we talked about end behavior. We talked about if the leading coefficient and the exponent was even or odd, what the graph looks like. In this case, we're going to look at what the graphs look like and some more things about them. We're going to be graphing functions as well. So this graph here on the right, we're going to be making a graph of that using some technology. So you're going to have to probably open a couple different tabs when you're working on the practice, when you're working on maybe through the video to kind of make sure you get experience and knowing what to do. So let's kind of get started here. It's going to be, it might be a kind of a long couple videos, but it's because it's all new material, and that's what the rest of Algebra 2 is going to be. Pretty much all new material for you guys. So let's talk about extrema. Let's get into example type number 1. Extrema, there are 4 different types. We have an absolute max, a relative max, or a local max. Either of those terminology or terms is okay to use. An absolute min and a relative min or a local minimum. We're going to use these 4 pieces of information. I'm going to give you the definition to all 4, and then we're going to locate as much as we can on the graph to the right that is provided. An absolute max, just like the name provides, absolute means the only, or I guess like the highest or whatever. Maximum obviously means highest, so this is the highest point on a graph. Highest point on a graph. Okay? If we look to the graph here to the right, okay, I have some high points, okay? And another thing we can call like a maximum is always going to be like the top of a hill. So it's the top of a hill. Now I got a lot of hills here. I got a hill right here, and I got a hill right here. But those, okay, are not absolute maxes because the graph actually goes above. So like this value is, if I would draw a line across, okay, this graph goes above that line. So is there an absolute max? Well, in this case, there is no absolute max because these graphs go up and up and up and up and up and up to infinity, and they're never at a single point. Okay? They're not at the top of a hill. They're just going to keep going up. They're never going to actually come and round to make that hill. So this graph does not have an absolute maximum. Well, what is a relative or a local maximum? Well, these are high points. So these are all high points that are not absolute. Okay? So high points, again, top of a hill. Top of a hill. So where's the top of a hill? We said it was right here and right here. Those are not the absolute. There isn't an absolute. Okay, so I have local maxes or relative maxes. So this is a local max. This is a local max. I like to use local because it's less words or less letters than relative. But if you wanted to write relative, you can abbreviate REL, and that's okay. What is an absolute minimum? Well, if an absolute max is the highest point, then an absolute minimum is the lowest point on a graph. And this is at the bottom of a hill. Okay, minimums occur at bottoms of a hill. Well, let's look at this graph here. Where are the bottoms of a hill? Well, if I'm looking here, this is the bottom of a hill, this is the bottom, and this is the bottom down here. But this point, the last one that I circled, that is the smallest value. Like the graph doesn't go below that value. And because the graph doesn't go below this value, this is the absolute minimum. You can abbreviate absolute as ABS, and you can abbreviate minimum as MIN. That's okay. Relative or local minimum. These are, again, low points that are not absolute. So what are some other low points? Well, this one here is a low point, and this one here is a low point. So they're a relative minimum. Okay, so those are relative minimums. All right, and so that's what I have. I have 2 relative mins, I have 2 local maxes, I have an absolute minimum, and I have no absolute max. So these are all extremas. In your graph, you can have a multitude of extremas. You could have 1, you could have 7, you could have 1,000,000. Now, we're not going to get that high, but you could. All right, so now let's get on to some examples that actually deal with some absolute mins and maxes. We're going to get onto a word problem and some other fun stuff. Okay, so now let's get into an example problem. Suppose we have a piece of cardboard that's 45 centimeters by 30 centimeters. We want to construct an open top box by cutting out congruent squares. Well, what does this actually mean? Here's our rectangle, okay, and what I want to do is I want to take each corner, and each corner I want to cut out a square. All right, I want to cut out a square, okay, and then that remaining, those cutouts, okay, what I'm going to do is I'm actually going to fold the box. All right, I'm going to fold the box so that I'm able to then like connect the box together, okay? So that's what I want to ultimately do. I want to do a couple things with that. So if I cut these out, technically this is, I'm going to fold on this dotted line, okay? I'm going to bring this side here kind of up into the box so it's like sticking out like 3 dimensions. I'm going to fold it right here as well. I'm going to fold it right here. Okay, and I'm going to fold it right here. So really the box that you're creating isn't that large. Like it goes from this big old rectangle to really now this really tiny rectangle because of how you're folding these to create that box. All right, and what I want to do is I want to look at the dimensions. I want to put the dimensions on this rectangle in places that make sense. All right, and then I want to find part A and part B. So 45 centimeters by 30. Obviously, the top and bottom are 45 because those are bigger. And then the side is 30. Okay? And the part A, it says express the dimensions of the box in terms of x. That means I want to use x when I'm finding the side length. So the length is equal to something with x in it. The width is equal to something with x in it. And then the height is equal to something with x in it. So now we got to think about how this is going to work. Well, if I have an x here, okay, that I cut off, and I have another x here that I cut off, I'm actually taking the whole side length of 45, and I am subtracting off 2 x's. Or I'm subtracting off x minus x, right? And that becomes 2x. Because I don't have those 2 little pieces anymore. I cut them out and I threw them in the trash. But they're all of equal value. And in the same instance, here on the 30, on the side of the 30, the width. Okay, so I have 30. I'm subtracting off 2 of those x's. And that is the width. The height is, well, if I think about it and I cut, okay, I cut these x's out, how tall... Because remember, I take this little piece here, this little rectangle, and I'm folding it up. So it's flat. I'm folding it up. And when I fold it up, how tall is it? Well, it's the size of x. However big x was, that's how big that is. So the height is x. Okay? Hopefully that makes sense. So then, so these are all my 3 there. It says write a formula for the box, for volume of the box as a function of x. So that means... in standard form, we'll talk about that. But write a formula. So what does that mean? Well, volume of a rectangular prism, which is what this is, okay, a box, it's length times width times height. Length times width times height. I'm going to do all my work up here just so I can have more work. Well, what is our length? Our length is 45 minus 2x. Our width is 30 minus 2x. And our height is just x. Well, it says write a formula in standard form. Standard form is when I multiply everything through. So I'm going to take these first 2 individual binomials. I'm going to put them into a box. So 45. I'm not going to do the box for you. I'm just going to show you what you need to do. 30 minus 2x. When I do all that math, okay, I get 45 times 30. I don't know what that is. 1350, right? Let me get out my calculator, I guess, and let's actually do the math. But I'm pretty sure it's 1350. 1350, 40, 5 times 30. I was right. Then I'm going to basically take these and combine those together. So that's going to be negative 60 minus 95. So that's negative 150x. And then 2 times 2 is 4x squared. All of this is going to be multiplied by x. And that is going to be 1350x minus 150x squared plus 4x to the third. So this is what you're thinking is the volume, right? And technically this is correct. But with the way the question says, it says in standard form. What standard form is you want the highest degree first, the highest degree first, and then you go down, and then you want the lowest degree at the end. So highest degree is 3, next one is 2, the lowest one is 1. So these, I actually need to like flip-flop the order on these ones. So the correct volume as a function of x in standard form is 4x to the third minus 150x squared plus 1350x. And that's the correct volume for this box, regardless of whatever x is, right? X can be different, and we'll find whatever x is, we can find the volume of this box by just plugging it in. All right, ladies and gents, this is example type number 2 for 5.4 polynomial functions. And you can see that the screen is actually a little different than normal because we're going to be using a website here to do the rest of these example types, example type 2 and example type number 3. And so I want you guys, okay, so what's going to happen is however you need to do this, if you want to listen to the video and pull this website up, this website is desmos.com. It's called Desmos, okay, Desmos. It is a free graphing calculator. You might actually have the app on your Chromebook if you go into the app tray and you actually look for it. It might be there, it might not. I'm not exactly sure if they've installed it. I know they were going to, but I don't know if they did or not yet. Anyway, if you go to desmos.com, this is what you will see on the right-hand screen. And so when you go there, you're going to hit Start Graphing. Okay, when you hit Start Graphing, this is basically what it's going to pull up as. You can either sign in to Google if you want to, or you can create your account. It doesn't really matter. You don't need to do that. That just saves all the stuff that you've been doing, and you don't need to do that, so that's okay. So, what are we going to do? Well, we are going to take this function, okay, this negative 5x to the 4 minus 95x to the third, so on, and we are going to find the zeros, the end behavior, and all extrema for that function, okay? And we're going to use Desmos to do it. So I'm going to come to Desmos, I'm going to click on that box here, okay? You can hopefully see what I'm doing. And I'm just going to start typing negative 5. And you can put x to the 4. Like if you wanted to do x and then you hit the shift 6 button, you get that like, it kind of goes up. But I don't have to do that. So Desmos is pretty cool, where it will actually just let me type. If I want 4 x's, x to the 4th, I can just type in 1, 2, 3, 4. And then minus 95, 1, 2, 3. Minus 525, 1, 2. Minus 245, 1. Plus 3, 4, 3, 0. Enter. So now what you have, kind of it looks in red. You can kind of see some red stuff on the graph to the right. And we need to look at that graph and figure out some things. Okay, so here we go. Here's how we're going to do this. Right here where I'm pointing, where it says hide expression list, those arrows that point to the left, you're going to click on that. Okay? Now, you can pinch your screen, zoom in and zoom out. I want to zoom out. So if you zoom in or you zoom out, you can see that your kind of graph is really crazy here. Okay, so here's what I'm going to do. I'm going to tell you how to type it in to make it a little nicer. And this for this function, you're going to have to do some stuff yourself to kind of figure it out. And I'll give you some strategies in order to do so. So here's what I'm going to do. I'm going to take these values where the graph kind of crosses the x-axis is between -10 and +10. Okay, -10 to +10. So I'm going to come up here to the wrench on the right. I'm going to change my x-axis from -10. I'm going to delete all this. -10 to +10. Okay, I'm going to change that from -10 to +10. Alright, so now it made your x a little bit more spread out. But your y values, okay, I'm going to do this. You can see that if I go back to the graph and I keep zooming out, I have like really large y values. Like the higher I go up, like it's crazy. It just keeps on going. And here's why it keeps on going. Look at the last value, okay? Look at the last value of the function. It was 3,000, all the way over here, 3,430. That means it's way up there at 3,430. So I'm going to go back to my wrench. I'm going to change my x-axis again because I changed it. That's why I just changed it. Let me change it back to -10 to 10. And then my y-axis, I'm going to change, okay, from, we're going to say -100 to +3,430. Let's make it a little bit bigger. Let's go 3,500. Let's go 3,500. And now, if I look at the graph, like that looks pretty cool. And I can zoom out now, and it looks a lot better, right? It looks a lot better. And the reason it looks a lot better is because now you have like what's going on in the function. You have the hills and the valleys and all that stuff, okay? So this is what I want. You have to do what you have to do to find the middle part of the graph. Alright? Now you can do this on a TI or you can use this on Desmos, and Desmos is free. If you don't have a TI, then this is what I want you to use. It's practice. You're gonna have to get practice on trying to find out what values on my x-axis and what values on my y-axis you'll need to use. You can't just hit a button and then it goes there. It doesn't work that way, okay? So, here's what I'm going to do. Here's what I need to do. I need to find a couple different things, right? The question said I need to find my zeros. I need to find my end behavior. And I need to find the extrema. Well, the extrema, remember that's mins or maxes. Oh, maxes. And then remember it's local or absolute, relative, right? We have those things. So here's what happens. I'm going to look at the graph and determine that. And how do I do that from a graph? Okay. On this graph, if you go and hover over the function and you click your mouse, you'll actually see a dot that actually happens. And if you move your mouse up and down, that button, that dot, is also going to move with it. If I click the graph, you will now see things that appeared, like little dots on the graph. If you hover over that dot without clicking, you will actually get the value, the x and the y value for each of those points. But we have to determine what those points actually mean. Well, this 3,500 in that space, okay, is the highest point on the graph. It's the highest point. And because it's the highest point, that's our absolute maximum. And what value is that? If I if I hover over it, I'm going to get negative 0.25. So parentheses negative 0.25, comma 3459.902. 3459.902. And that is your absolute max. You don't have to do any calculation. You literally just type it into Desmos. You have to then mess with your window, and that's the hardest part. But then Desmos will do it all for you. Okay? What about zeros? Zeros, remember in the last video for 5.3, we talked about these are where it hits the x-axis, the graph. Well, where does the graph hit the x-axis? It hits right here at 2, 0. Again, hovering over it at 2, 0, so that's one answer. So a 0 is 2, 0. And if I actually look at the graph again, it touches right here as well at -7, 0. -7, 0. And this function, okay, this function is, or it doesn't have any local mins, or local maxes, or absolute minimums. This is the function. If I were to zoom out as much as you wanted to, okay, let's zoom out. If I were to zoom out, that function, like that red stuff, just keeps going. That graph just keeps going and going and going and going. So therefore, we know the function like stops right there, like it doesn't go any further. Okay? How do I write that? Remember the end behavior from the last video, from 5.3. So the end behavior, I'm going to write this down here just for space, is as x gets larger. As x goes in this direction, what's happening to the y? The y is going further down. So as x approaches the bigger number, f of x, or the y value, approaches -infinity. And then as x gets smaller, it goes in this direction. F of x also gets smaller and goes down. And so this is my end behavior. This is the extrema. This is the zeros. And all thanks to Desmos, because you didn't have to calculate anything. Okay, let's do the next one. Let me clear all this stuff out. Okay, now how do I do the next one? Well, what I'm going to do is I'm going to open my arrows up here. I'm going to hit the X here, and it clears out my graph. And now I'm going to type in my new graph. -4 xxx plus 72.6 xx minus 327.2 x plus 430.5. Once I did that, I'm going to close it out, or I'm going to close those arrows. And now my function looks like this. It looks pretty cool. Okay, it looks pretty cool. So now let's find your zeros, your end behavior, and your extrema. Again, we're using the graph. If I click on the graph, sudden dots appear. I got dots that appear. I got dots. I got dots. I got dots. If I zoom in a little bit, you can see those dots like make more sense, right? I got a dot here. I got a dot, dot, dot. I got another dot over here. And if I go over here, I got another dot right in there. Okay, so let's zoom out a little bit and find out what those dots are. Let's move this up here so I can do some stuff. Well, it looks as though this point in this area, wherever that dot is, I'm going to say that dot is right there, okay? Wherever that dot is, this is our local max, because it's at the top of a hill, but it's not the highest thing, because this graph actually goes up and up and up and up and up. So that's our local max. Now what value is that? I can hover over it and I get 9 point, let me delete this. I get 9.105. So this is our local max. 9 point, gotta do some stuff here, 105, okay? 9.105, comma, 450.703. 450.703. That's your local max. Now some of you might be like, well, you found the graph really nice. Like, you found it pretty fast. How am I supposed to do it that fast? Especially, let's clear this graph out. Let's do this. Let's do this. Let's do home. Okay. When you type this in the first time, if you just got to Desmos and you didn't mess with your wrench or anything, this is what it's going to look like. This graph here doesn't look anything like what I just graphed. Okay? So, if I look here now, I have a dot here, and then a dot over here. So I'm going to zoom out. I'm going to zoom out. Okay? And I always want to be on the negative and positive side of things, so I'm going to put the wrench. I'm going to go from -10. -10 is just a good number, okay, to kind of start with. And then your max, I can't go to positive 10 because this line over here is actually bigger than 10, so I got to go further than it. So I'm going to go to 20. Okay? So I got from negative 10 to 20. What about my y-axis? Well, my y-axis, like negative 10 is a good one to start with because the graph, it looks like, is not quite at negative 10 yet. Negative 10, sorry. And then what about my bigger y value? Well, that's where the last number is going to play a big part. 430.5. So it's got to cross at 430.5, so I'm going to make a number bigger. I'm going to go to 500. Okay, now I get off of this, and now, look at this. I got a good graph. If you wanted to make your graph a little bit more spread out, you could change your x's to negative 5, and you want to change your x over here to 15. And now it's even spread out way more than that. Okay? So we got to play around with our spreading out of our x's and y's, kind of condensing the graph or making it, expanding it. Okay? So just be aware of all that. Now, what do I want to do? I want to find, so this was our local max up here. It looks as though this is the bottom of a hill, right in there, this point. Well, what point is that? Okay, what point is that? That is the point. Click on the graph. That is the point 2.995. 2.995. So it is a local minimum at 2.995, comma, negative 5.701. Negative 5.701. Those are our two mins or maxes. In this problem, we do not have an absolute max, and we do not have an absolute min because the graph, if I zoom out over here, keeps on going up and down forever. Okay, it doesn't stop. So now let's look at zeros. Zeros are what? They are values that cross the x-axis. What are they? Click on the graph. It'll tell you. You hover over where it crosses. Whenever it's whenever it's a 0, the y value is 0. So what's the x value? Okay, that's what I want to find out. So I want to find my zeros. I got 1 0. It looks to be 2.608 comma 0. 2.608 comma 0. I got to find the other 2 because it looks like it crosses 3 times. I got 3.398 comma 0. 3.398 comma 0. And it looks as I have one more. That's 12.144 comma 0. 12.144 comma 0. Those are my zeros. Again, hover over the graph, and that's it. There's another dot here that I have not messed around with on this graph and the other graph. It's this one here. This is where the graph crosses the y-axis, so we consider that a y-intercept. So just in the future, that might be important. So our y-intercept here is 0, 430.5. It's always the last value in each of the functions. Okay? It's just always the last one. If there's no variables there, it's always the last one. I'm not concerned with it now, but in the future I could be. Well, what else we got to do? We got to do end behavior. End behavior. So what's going on with the function? As x gets larger in this direction, the y value is going down. So f of x goes to negative infinity. It goes down. But as x gets smaller and goes this way, the y value gets bigger. So f of x is going towards infinity. Okay? That's it. I know it's a lot, and I know this video is a little long, but I'm showing you how to use Desmos for the very first time, most of you. So just, that's why it's long. It's not that it's hard. It's just you have to plug in the numbers into Desmos correctly and manipulate the graph so that you're able to get what you need. Okay? Even if you were to take this graph, all right, let me do some stuff here. Even if you were to take, sorry. Even if you were to take this graph, okay, and then go really kind of crazy, like zoomed out, you can still click on it and it'll still give you some points. But it looks like there's only 1 point here. It looks like there's only 1 point here, but if I keep zooming in, now there's 3. So that's why you got to kind of be zoomed in, but zoom far enough out so you can see what's happening. Example type number 3. At this time, you're like, what did I get myself into? Like, why do we got to do this? This is a standard, and we could do it like using actual mathematics to find all these mins and maxes, but this is much easier than that, so you can thank me later. You know, I know it's a little difficult, which is fine. It's okay to have difficult things. Yeah, so let's get into this last example, example type number 3. This is a word problem. And if I look at it, it says the average price of gasoline can be modeled by the cubic function, which is right here, where C of t is the price in dollars and t is the number of years. So basically, this equation, since the year 2000, way before you guys were born, this equation can be used to model the price of gas based on what the t value, how many years it is. So this would be 2020, right? Or 2019 last year, or 2015. So 15 years from 2000, okay, would be 2015. That would be 15, so t would be 15. All right, so here's what I want to do. I want to take this function and I want to use Desmos. Again, I'm going to go back to Desmos. I'm going to type it in. Now, so it's negative 0.00225. Now, when it says t to the third or t to the 2, I can't graph using t's, but when I write functions, like in terms of mathematical functions, t is a very popular value to use, but when I graph it, I just use the letter x. So I use xxx plus 0.04208 xx minus 0.0151x plus 1.4337, enter. I'm gonna, once I make sure everything's all good, okay, I think it's all good, hopefully, I'm gonna hit the double arrows to close it. I'm gonna now follow the instructions, because part A, it says graph the function in your calculator, which you did, but using the domain of 0 to 20. So what does the domain mean? That's our x values. I need to go to my wrench, change my x-axis from 0 to 20. Hit enter. Now I go back to my graph. Okay, now I'll go back to my graph. What does the sketch of this look like? Well, if I actually sketch it out, let me do that. If I actually sketch it out, where are we at? Right there. Okay. I have the y-axis and the x-axis. This is 0, and this is at 20. And the function looks like it's kind of going up, and then it's hitting its maximum, and then it's coming down like that. That's what the function's doing. That's all you're doing for part A. You're just sketching the function. It doesn't have to be exact. Just got to be a sketch. Well, describe any extrema in end behavior. Okay, what's going on with this function? Again, extrema, mins or maxes. Come to the graph, click the graph, and you get a point here. 12.207 at 3.349. That's an extrema. So extrema, this is a local max, was what? 12.207. 12.207 comma 3.349, I believe. 3.349. Oops, 349. So that's a local max. And if I were to zoom out a little bit in this function, or move the function over, you can see that the function actually has a minimum of this one here. This one is the y-intercept. This is the minimum, 0.261, 0.261, comma 1.431. 1.431. This is a minimum. Okay? Local min. Local min. Or relative min, that's fine too. So now I'm going to go back and I'm going to make it so that it's right there. Alright, fantastic. End behavior. Well, what's going on? The further x gets, so as x gets larger, if I were to zoom out of this function, y actually gets smaller, right? It goes down, 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 down. Okay? So what's going on? Well, as x gets larger, f of x gets smaller. So what that means, think about this. Okay, think about this is what the graph is actually meaning. Right here at 0, 0, where it crosses the x-axis and the y-axis, right there, okay, that is at year 2000. So according to this model, the gas prices in 2000 was $1.43 a gallon. Think about that. Like, you guys are probably driving, or your parents are driving, right, and you're spending $2.40 a gallon. This was $1.43 a gallon. I started driving in 2002, and for some reason in Connecticut, where I'm from, I was able to get it for $1.31 a gallon. Okay, some like gas station just opened up and they were running like promotions. They wanted to get business, so they were discounting gas at like 25 cents a gallon to try to get business. Okay, the further and further you get away from 2000, so right here at this point, when x is 2, 1.54. That means in 2002, gas is $1.54 a gallon. Like I said, my place, they were discounting at like 20 to 25 cents a gallon. So that's about $1.30, right? Now, at year 12, which is 2012, gas is $3.34 a gallon. Holy cow, that's a lot of money. Which actually, that was about right. Okay, about 8 years ago, that was about right. The highest peak was when it hit the maximum value at a little over 12 years, 0.207 of a year. So 12.207 of a year, it hit $3 and almost 50 cents a gallon. And then, since then, it started to now decline. So as further I get, it's starting to decline. Okay, that's what is actually happening. The further you get away from the 0, it's going to raise, and now it's going to start to lower. So where are we at? We're in 2020. So actually in 2020, according to this graph, gas prices would be negative. That's crazy. That means you go fill up gas, and they pay you to take their gas. That can't happen, right? So this function is only good until 2017. So this function is only good until this value right in here at 17, 2.17. So in 2017, about 2 years ago, 3 years ago, gas prices were about $2.17 a gallon. They're a little higher now, but 3 years ago, that's what they were at. Okay? So now, let's look at the zeros. The zeros of this function is where it crosses the x-axis, right? So what value is that? Hover over it, 19.839, 0. 19.839, 0. So what do the zeros represent in this model? They represent when gas would be free, right? I wouldn't actually have to pay. That's free. Like, I walked up to the gas station, I'm like, yo, I need $10 and pump 17. And they're like, gas is free. You can get all the gas you want. And you just, you get 37 gallons of gas and you ain't got to pay nothing. Man, that'd be great. That would be great. Let's reminisce a little bit. Okay, enough time for that. Let's get into part D. It says this model was created in 2017. So using it, predict the price of gasoline in 2020. So now, let's do what we just did. Find 2020. How do I do that? I'm going to go to my function. I'm going to click and drag my dot to where I get 20, which is right there. 20, negative 0.164. So 20, negative 0.164. Predict the price. What does that mean? How accurate is that? Well, that's not accurate. It is 2020 right now. And there's no way when I walk into the gas station, I go to your friendly 7-Eleven, every gallon of gas that I get You mean to tell me they're gonna pay me 16 cents to get their gas from their gas station? That's crazy. I wish that was true, because gas is kind of expensive, but that's not gonna happen, right? That's not gonna happen. So what we're doing is we're going beyond the given domain. It's called extrapolation. We want to explain why extrapolation can be dangerous when predicting future events. So this function is only accurate to this point right in here. Anything further than it on the x-axis, it's not accurate. Okay? It's not accurate. So why is that dangerous? Well, it's dangerous because the values of whatever you're doing could increase or decrease, right? So the values of gas in this case, according to this model, are going to decrease, but there's no way in our society, no matter what country you live in around the world, gas is ever going to be free. Like, anytime you want something, you got to pay for it, right? You go to the store and you want bread, you got to pay for bread. Man, you want that nice milkshake at like Steak and Shake, man, or 7-Eleven. I'm kidding. 7-Eleven, they got milkshakes? I don't think so. Culver's got some good, like, concrete mixers. Man, I love some ice cream. But they're not going to just walk in and give it to me unless I got some sort of coupon or something. All right? That's why extrapolation is dangerous. It could put people out of business, or prices, certain things can skyrocket based on what the model is saying. Okay? That's a little complicated to understand, but think about it in terms of, right, the x-axis in this case is years, the y-axis is money. Money per gallon of gas. All right, that's it for this video right here. Deuces.